Thank you. And my name is Victoria Firsanova. And well, let's get started. Let's start with a short recap and let's remember what text-to-image models are. So we have a prompt, which is an input for our model. For example, a cat eats sushi with two giant muscle cars. I hope many of us tried such fun experiments with those models. And we have a model that we want to generate. We want to generate with that model some image that capture this prompt. So for example, if we want our model to draw a cat, we give it in our prompt. And we have some fancy result like here. From the point of view of natural language processing, one of the most interesting facts about text-to-image models is that have a so-called hidden vocabulary, some internal linguistic structure that manifests itself in the outputs of those models. And some of the research shows that such models, when such model generates image with some caption of it, we can use those captions as a prompt to generate some new things. And some research shows that this model can generate some pretty fancy names, for example, for birds, such as on this slide, which is called something like apoploe, which doesn't make any sense in English or in Latin, but it can make sense for the model itself. And if we ask the model to generate this strange thing called apoploe, it will repetitively generate some kind of flying objects or a bird, to be more precise. And this amazing exploration, it studied some kind of a response to conversation on social media, and different ML researchers on Twitter or other platforms like Slack communities were discussing why the model started to generate those strange hidden vocabulary units. And users online tried to make tokenization and of that prompts, and they found that those words like apoploe were not really random. They had these pieces that indicated some families of birds, and that is why the model associated these strange prompts with birds. And I decided to make a deeper analysis of that behavior, and I have analyzed some evidence of finding linguistic structure in large linguistic models like BERT and other transformer models. And I decided to use those knowledge to make something like a semiotic and linguistic analysis of text-to-image models. So my research is pretty novel for me as well. I would say that it is a pilot research which covers different problems of explainable AI. And I made a hypothesis that text-to-image models that can generate text, first of all, are culturally biased because we're working with images, and different data sets are, of course, culturally biased because they are built on human data. And second of all, they must be conditioned by different linguistic generalizations, just like autoregressive language models such as GPT or other examples. So what I decided to do, first of all, I decided to use some magic, but to be more precise, I decided to use prompt engineering. Prompt engineering is a technique that allows us to create some prompts that will lead to some efficient image or other generation. So prompt engineering appeared with the spread of large linguistic models such as GPT family, and then it became more and more widespread, and it is actual in text-to-image modeling as well. Then I decided to use those prompts to generate some samples with different architectures such as GAN and transformer-based VQGAN plus CLIP. and diffusion models such as Stable Diffusion and DALL-E 2. Then I decided to make some feature extraction by creating heat maps and tokenization, like we saw on previous slides with social media reactions. And to conclude all this journey, I decided to make a classification of the samples by using the knowledge from linguistics and semiotics. So the first question that I had is which languages to choose, because I decided to focus on multilingual study. Modern natural language processing really lacks studies on multilingual exploration. Most of the studies are focusing on English data. And I decided to cover as many languages as possible, but it is known that there are numerous languages in the world, and I decided to use some classification system as a baseline. So I decided to use the classification of writing systems because when we talk about text-to-image modeling, we are still focusing on computer vision properties, on image generation. And for me, it sounds quite logically that writing systems, different scripts are the first thing that such a model should capture. So here you can see this one of the classification of writing systems. And I also selected several languages that represent each of the script type. And this selection is based on the most represented languages online and on different data sets such as Common Crawl. So I created a baseline prompt, which looks like subject in language. And I created two lists of the subjects and list of languages. List of languages was shown on the previous slide. And the list of subjects is as follows: text, word, and caption. So for example, I asked my text-to-image models to create some random text in Hebrew, for example. Now let's dive in the models that I used. So DALL-E 2 is not an open source is not an open source model, but it is extremely robust. Stable Diffusion is an open source model, which opens up a lot of opportunities to tune and reproduce our results as well. But of course, it might be not robust in generating text, because this is a trivial task. This task is not trivial for text-to-image models. And the last, but not the least, approach is Wikigam plus Clip, which is also open source and might be slightly predictable because GANs, they might be more a bit more explainable, maybe because this technology is is better explored yet than diffusion models, because diffusion models are stochastic in nature, and that is why it's harder to reproduce those results. So let's move on to the results of this study. So those are some of the heat maps that I made with diffusion attribution attention maps. And this is an example for the prompt text in Arabic. We can see that the word Arabic itself is the most important part for stable diffusion and other diffusion models. While the word text is also pretty important for generating this image. And we can see that this example is slightly culturally biased because it reminds us of some religious texts such as Quran, because we have this something like a frame which reminds us of religious texts. Next, I did the tokenization, and what I found the most important is that during the tokenization with byte pair encoding, which is the basis of the clip embeddings, I found that the model had highlighted these adjective affixes or something like that. pretty similar, which means that it is important for the model that these last words, Russian, Arabic, or English, or whatever, is adjective, meaning that it is not just Russia, for example, but it is Russian, meaning that it is an attribute of Russian culture, for example, Russian language. And here are the results of my classification. So first of all, I found some generative repetitiveness of the results. For example, this is a result for text in Korean, and we can see that first 3 lines are absolutely the same, while there are some little differences. So each symbol is unique if you will watch it more carefully. And this behavior of repetitive generation is quite widespread in different generative approaches, such as recurrent neural networks like LSTMs and generative neural networks like GPT-2 and even the newer versions of GPT. They are pretty repetitive. And this is pretty interesting. I think that is a common generative behavior because when we are working with diffusion models, we are working with image generation, and those are generative processes as well. The next class is some human readable items. For example, I found that even if I asked the model to generate text in Greek, for example, it wanted somehow to generate the word Greek itself in English, meaning that English is still a dominant language for many models. Another interesting example is when I asked a model to generate a text in Japanese, but it has generated, I suppose, kanji and romaji. So those are Latin script in Japanese. Or maybe it has generated English, but it is really hard to predict here because the generation itself is not finished here. It is somehow incomplete. Cultural bias is, my hypothesis about cultural bias is proved because here we can see a lot of examples in different diffusion models, in Stable Diffusion and DALL-E 2 as well. And here is the example for text in Yiddish. We can see clearly that it is some kind of a newspaper, and there is a photo of some gentleman, and there are still many religious texts that are associated with Arabic, and that is something like a Scrabble game for English, which is also something associated with English culture. And this is a text in Russian, which reminds us of Russian schooling system. We have a pencil and a very widespread type of a copybook in Russian culture. Another interesting example, which occurred in Stable Diffusion model only, is a landscape generation. So instead of generating some text or script, the model tried to generate some kind of a public space. And again, we can see that there is something connected to the religion topic, for example, or historical building. For example, here is text in Greek, and the model generated something like a Greek temple here. While this example is a text in Russian, and we can see some USSR landscape. So let's move on to the conclusion. How do text-to-image models perceive the natural languages of the world? So first of all, the study shows that both diffusion models and GANs can reproduce different scripts. And the models do scan the cultural context, which manifests itself in images of some written sources or public places, or even in some religious contexts. We can see that words that are generated or resemble some English text in DALL-E 2 are really human readable and even make some sense, like the word Greek in a huge lettering. And also, we can see that DALI2 captures common letter combinations and basic grammar units. For example, here, we can see something like an indefinite article and. Overall, in the future, we expect to observe more NLP abilities in text-to-image modeling. And that means that it can be used in different kinds of cybercrime, like fake reproduction or fraud. And this problem is important nowadays. So this study might become a contribution to cybersecurity research. However, even today, we can say that we can detect fake images that contain text by excessive repetitiveness, explicit cultural bias, and different artifacts. For example, the model cannot handle small font. And now I will be happy to answer your questions. Thank you.
So, Victoria, thank you. Thank you for your talk. And please, if you have questions, raise hand. So, okay, then let me start. Could you please go to the slide where you've been recognizing Arabic scripts? Yep. Maybe I missed a bit, but usually the problem of recognizing something looking like this is really tough. Like the numbers I've said really is small enough because actually the accuracy is super low. So I actually couldn't get, did you manage to, the model managed to recognize Arabic here, or I'm mistaken?
Thank you for the question. So let's start from the very beginning. We can see from this image that the whole image contains only a piece of Arabic text, and it is surrounded by something like a frame, possibly a frame of a religious book, but it's just my guess. So we can see on the last frame that the model does associate this text, which reminds us of Arabic script, and it identifies this Arabic script in the middle of this picture, which is this white background with black letters on it. So that shows that the model does differ Arabic scripts from other pieces of this image. It doesn't mix this frame and the other parts with the text itself. And the word text is also highlighted in red, meaning that it is also associated with Arabic script here. While the frame and something like a background is not highlighted.
Mm-hmm. So, but what is the conclusion you make? Because actually we see that, for instance, the picture with text, there is just a third of the real text is highlighted with red, or maybe less. And even if we go to Arabic, we can see that half, maybe a little bit more, of actual Arabic text is highlighted with red. So what is
well, I think that here we should focus on the fact that the model highlighted most, a significant part of this image as Arabic script, because it is not quite precise here, but I find it's important that it didn't highlight the frame as Arabic, for example, meaning that, in my opinion, this somehow shows that the model understands that the script is more important for the generation than the word text. So for the model, it is more important to generate something that reminds us of Arabic culture or Arabic script or something like this than to generate some kind of a text.
Okay, I see. So yeah, thank you.